Okay, welcome to the Chapter 9, Data, Voice, and Cabling 3rd edition, Testing Voice Data and Video Wiring. Now, what's the goal in this chapter? Well, our goal is that you would understand the methods of testing coax and twisted pair cables. Now, it's important to understand that all wiring installed for voice data and video or video applications needs testing to ensure proper operation. Data and voice cabling are similar in testing requirements and are covered in one section. Now, coax testing can be either easier if it works or much harder if it doesn't. So we're going to cover that one first. Now, what's important to understand that coax has only two conductors. It's got the inner conductor and also the shield, continuity and no shorts. So this can be tested by a simple coax tester or a digital multimeter. With the digital multimeter, testing the cable with no terminations will tell if the cable is shorted, and testing with it terminated will tell whether or not it's open. Now, if the cable passes these tests, it should work with most applications. Now, sometimes coax can be damaged in the installation and will have usual attenuation characteristics over its frequency range. Now, if a coax cable has problems transmitting a signal, but shows neither an open nor a short, look for damage like kinks that may be causing the problem. Now, when it comes to unshielded twisted pair testing, testing the voice and data with UTP, wiring is a function of use. Unless the network running on the wire is high speed, the wire only needs testing for correct connections using a low-cost wire checker or a toner, also called a WAN. Now, as the network speed increases, the need for testing performance at high frequencies or appropriate network speeds becomes mandatory. Voice cabling requires a simple verification of the connections called wire mapping. Now, this is done with a simple instrument that plugs into the cables at either end, which tests for a proper pin-to-pin continuity. A toner is a device that puts a toner on the wire and then allows checking continuity at any point with a small receiver. They can be used to trace and identify wires in termination blocks as well. Now, even though voice wiring may not require more than continuity check, many structured wiring systems pull the same Cat5 or 6 cabling for both voice and data applications. It's because the incremental cost of Cat5, 3, and 6 over Cat3 is low, and the installation of the same cable everywhere gives the most future flexibility. Therefore, it may be appropriate that all new wiring is fully tested, as if any link may eventually have to carry high-speed network data. Most testing today, with the exception of simple wire mapping, is done with automated load testers of two types called certification testers and verification testers. Certification testers are pre-programmed to perform tests to the exact requirements of TIA cabling requirements or cabling standards. These instruments test wire mapping, length, attenuation, and crosstalk according to the methods specified in the cabling standards. Verification testing verification testers run actual network protocol tests over the cabling to ensure cabling will carry network traffic without errors. As long as the instruments meet the standard requirements and are designed for testing, the cabling systems or the network protocols are proposed for the cable plant that you're installing. You can expect valid test results and generally accept pass or fail results. Crosstalk is typically, in my experience, has been the most difficult test to pass, especially for Cat5e and Cat6a standards. Wire mapping includes all tests for corrected connections. The correct pairs of wires must be connected to the correct pins according to the color codes defined by the standards, either the 568A or 568B mapping. There must be no transposing of wires or pairs and no shorts or opens. The 568A and B standard may be used for building wiring. The T568B standard is more commonly specified by AT&T. The only difference between A and B wiring is the crossing of pairs or swapping of pairs 2 and 3. And swapping those pairs, which makes no difference in performance. It's simply a different color code convention adopted by various vendors. So it's the white-orange pair and the white-green-gray. So it's your wires 1 and 3 and 2 and 6 would then be switched. Whichever version you're going to use, it must be used throughout the entire installation to prevent problems. Some plugs and jacks include both A and B wiring guides on the part. So be careful that one end is not wired to a different standard. If you do end up with one end being 568A and the other end being 568B, you would have what is called a crossover connection, which is a connection that is used to connect similar devices like a PC to a PC or a switch to a switch or a router to a router. There is another variation of the 8-pin connector pinout, and it's the Universal Service Order Code, which is the RJ61X, which is used for voice only. Next thing I want to discuss will be problems that you may run into. In most wire map problems occur at the connections themselves. Typically, physical examination of the connections should find the fault. Wire map errors fall into several basic categories. One would be a short or an open. Now, a short occurs when two conductors are accidentally connected, and an open is where one or more short wires are not connected to the pins on the plug or perhaps at the jack. Now, a short is what we're looking at up top, the first one, 1 and 2, where we end up having the two wires connected to each other, so they're shorting each other out. And then if we look at pair 2 with wire number 6, you'll see that there's a break in the line. So the wire never really made to the end of the connector, and that is what we call an open. Okay? Opens can also occur due to cable damage. So a TDR, which is called a time domain reflector, which sends a signal down the wire, then bounces back and gives you the distance. So if we're sitting here and we have 8 wires that are showing 75 feet in distance, and you have, or 7 wires that are showing 75 feet in distance, and 1 wire that shows 35 feet in distance, we know that that 1 wire has a break in the line. A reverse pair occurs when the conductors, the tip and the ring, are reversed in the wiring orders. And then we have a transposed or a cross pair. Transposed or cross pairs occur when both conductors of one pair are swapped with both conductors of another pair at the other end. The most common cause for cross pairs is termination on one end with the cable 568A and the other end being 568B, which, as I mentioned earlier, would end up being a crossover cable. A split pair, and we use a wiring verifier, will provide basic connection information, but some faults, like split pairs, may show up in a wire map. Split pair occurs when one wire on each of 2 pairs is crossed at both ends. This fault is impossible to find with a normal wiring verifier because the wire map is correct. That is, meaning that the pin connections are correct, but the wires are not in the proper pairs. Split pairs can be detected only in a crosstalk or near-end crosstalk test, where the unbound pairs can be detected. Split pairs are usually caused by terminating a jack with punch-down color codes 1, 2, 3, and 4 instead of 568A or 568B, which splits pairs 1 and 2. Now remember that these miswirings can occur in any combination, and a common error is simply mistaking the color coding and the mixing of wires. Another common error is terminating a 568A on one end and a 568B, or a USOC, which is strictly for video, on the other. The wire mapper should detect those errors. Another problem we might run into would be impedance, resistance, and return loss. It's important to understand that impedance is the resistance of the cable at the frequency of signals transmitted. Return loss refers to reflections that occur at changes in impedance. These reflections can cause errors in signal transmission if they're too large. Unshielded twisted pair cable is specified to have a nominal impedance of 100 plus to a negative 15 ohms. For high-speed data, both impedance and return loss are functions of the signal frequency, and impedance tends to decrease with frequency. Cable connectors and other hardware for high-speed networks are designed to have very consistent impedance to prevent reflections. So for cable, that means having the size of the conductors, the twist of the pairs, and insulation materials carefully controlled. The term structural return loss is used to refer to the reflections caused by variations at the impedance of the cable itself along its length. Even variations in production of cable can result in varying impedance, so consistently using the same cable in a network can minimize the problems. At connectors, the twist of each pair must be maintained to within a half an inch or 13 millimeters of the connection points to prevent crosstalk and undesirable reflections. If one expects consistent high-speed network performance, every component in the cable plant must be rated for Cat5 and installed precisely. Cable length needs to be known to verify that the length is within the limitation of the design standard and for future reference in moves, changes, or troubleshooting. The length of the cable can be estimated by measuring resistance as described in the preceding text, or by using a time domain reflector. Time domain reflectometry works like radar, sending an electrical pulse down the cable to an open end where the signal is reflected back to the transmitting end. By knowing the characteristic speed of the signal in the cable, called the nominal velocity of propagation, and the round-trip transit time, you can calculate the length of the cable. Now, the NVP is an average value. Actual cable samples may vary as much as 10% among production loss. Even each pair, which has different twist ratios to reduce crosstalk, will have a different velocity of propagation, varying as much as 3 to 4%, and a different physical length. So add to this the inherent inaccuracy of the instrument, add another 2 to 3%, and you'll see that the measurement is a good approximation of the length, but not an exact measurement. All testers will measure and report the length of each pair. As an electrical signal travels down the cable, the impedance causes attenuation. At the far end of the cable, the signal will be smaller than at the transmitter. It is important that the attenuation be less than a specified value, so the received signal is of adequate strength for proper data transmission. Attenuation is expressed in decibels, where 20 dB, or decibels, is an attenuation factor of 10. As with everything else we've talked about, attenuation is a function of frequency, increasing at higher frequencies, and must be tested at operating frequencies. Testers will test at the frequencies specified in the category of cable being tested. Up to 60 MHz for Cat3, which is hardly used in our industry anymore except for telephones, 100 MHz for Cat5e, and 250 MHz for Cat6, and even higher for 6A and 7. Measuring attenuation requires an instrument at each end of the cable, one to transmit a known value, and one at the far end to measure the signal level and calculate the attenuation. Pass-fail criteria are set by the 568 standard. In short, the easiest definition that I try to give, attenuation is the weakening of the signal over time and distance. Now, in a cable that has 4 pairs of electrical conductors, whenever one pair is carrying signals, it may couple some of its energy into an adjacent pair. Now, if a signal is being transmitted from another end, simultaneously, the proper signal may be compromised by interference by the crosstalk. Each pair works like an antenna. The pair carrying a signal is the transmitter, and every other pair becomes a receiver. The cable construction, including the variation in twist rates in the pairs, is designed to minimize this phenomenon called crosstalk. Like everything else, crosstalk is frequency dependent, so it must be tested over the full frequency range specified for the category of cable being installed. Now, as stated earlier, at the connectors where crosstalk is most critical, the twist of each pair must be maintained to within a half an inch or 13 millimeters of the connection points to prevent undesirable reflections. If one expects consistent high-speed network performance, every component in the cable plant must be rated the same and installed precisely. Testing crosstalk is quite simple. Terminate the far end of each pair to prevent reflections that would interfere with the crosstalk measurements. Transmit a signal on one pair, measure the coupled signal on another pair, and calculate the crosstalk in dB, just like attenuation. As with attenuation, pass-fail criteria are set by the TIA 568 standard and are given in the following discussion on certification. And note that each pair must be tested against all other pairs for a total of 6 tests, and the test must be repeated at both ends of the cable for it to be valid. The most common failure for next or near end crosstalk is improper termination. If the twists are not maintained within a half an inch of the termination, the near end crosstalk will fail. Poor quality components, including patch cords, termination blocks, plugs, jacks, or cables, will cause failures also, especially with high frequencies. As mentioned earlier, split pairs will cause unbalanced transmission and high crosstalk. It is with near-end crosstalk testing that you will most likely find those problems. Ethernet and token ring will use only 2 pair out of the 4 pair UTP cable. Some of the new higher speed networks like gig and 10 gig Ethernet use all 4 pair because they transmit over multiple pairs simultaneously. Crosstalk occurs from several pairs at once. It can be a bigger problem and needs testing. The power sum near-end crosstalk measures crosstalk on one pair while all other pairs are transmitting. In a duplex communication link, like networks running on UTP cabling, signals can be traveling in both directions simultaneously. Thus, at the receiver end of the cable, one can have a signal from the other end attenuated by the cable, and crosstalk coupled with the local transmitter, simultaneously arriving at the receiver. Now, because both ends transmit signals of approximately the same amplitude, we want the received signal to be higher than the interfering crosstalk, which gives attenuation to crosstalk ratio. It's the measure of this situation and an excellent indication of the overall quality of the cable link. For example, if the crosstalk is 35 dB and the attenuation is 15 dB, our received signal will be 20 dB larger, a factor of 110 than the crosstalk. If the crosstalk is 28 dB and the attenuation is 22 dB, then the received signal will be 6 dB larger, factor of 2. Thus, the higher the ACR, the better cabling performance. Far-end crosstalk is much like the near-end crosstalk, except it's measured at the opposite end of the test signal. Because the test signal is attenuated more on longer links, far-end crosstalk may be greater on shorter links. To normalize the measurement, we have ELF E XT, which compensates for the attenuation of the signal. The next thing you want to talk about is what we call alien crosstalk. Now, the consequence of higher frequencies needed for 10 gigabit Ethernet augmented Category 6 cabling, or Cat 6A, was found to exhibit a new form of crosstalk. And at these frequencies, signals would couple from a pair on one cable to the same pair on an adjacent cable, whose twist ratio matches that of the transmitting cable. The problem is worsened by bundling cables in cable trays, a common practice and can be found in Cat5e and 6 cables tested under conditions specified for certification for usage on 10 gig Ethernet. Testing for this problem, called alien crosstalk, is being specified in standards and incorporated over new certification testers. The test process is tedious and time-consuming, requiring testing several cables bundled in the cable under test, but is an issue as the frequencies being used for data transmission. In personal experiences, I have had the difficult time in testing Cat6a cable for 10 gig, and the alien crosstalk is probably the reason why. Next we want to look at is propagation delay, or simple delay. It's a measure of the time it takes for an electrical signal traveling at about 2/3 the speed of light to reach the far end of the cable. Testers measure delay as part of the process of measuring length. Now, because each pair has a different length due to the twist rate and a different NVP, there will be variations among 4 pairs. This is not a problem with most networks because the signals are carried on only one pair in each direction. However, many of the high-speed networks, 100 meg and higher, are using 2 or even 4 pair in each direction. So if the parallel signals arrive too far apart, data errors will occur. The design of the cable having a different twist rate on each pair of wires, a more tightly twisted pair will have slightly longer wires or for a given cable. Thus, a signal will take different times to reach each end. And an NVP can also vary with wire installation, also causing differences in transit times. Some cables have been built with different or cheaper installation on the pairs and not normally used with Ethernet token ring, and the variation in transit times may be more than tolerable. Next, we want to talk about certification versus verification. The industry standards covering structured cabling includes a full set of test standards for UTP cabling and have been designed into instruments called certification testers. These instruments test wire mapping, length, attenuation, and various components of crosstalk over the full frequency range of the category rated cable, with the actual test specified dependent on the rating of the cable. Automatic certification testers give you a pass-fail result, an indication of the uncertainty of the result, and diagnostic information and troubleshooting. Certification testing is totally based on cable standards. Length testing requires that the link be less than 90 meters and the channel itself be less than 100 meters, including the test equipment patch cords. Wire mapping requires terminations for 568A or B, USOC or other terminations, while perhaps valid for the installation, will not meet the 568 standards. Certification testers will ensure that the cable plant will meet standards for the cabling, but not network standards like Ethernet. The assumption is that if the cable plant is compliant with the standard and the networking equipment complies to its appropriate standard, the system should work. This assumption led to the development of another type of tester, the verification tester, that actually tests the cable plant by running network data over the cable while testing its operating parameters. These testers test for specific networks, for example 10, 100, and gig Ethernet. They are simpler instruments and cost a fraction of the price of an expensive certification tester. The choice of which tester to use is up to the user, depending on whether the orientation is to installation of a standardized cable plant or a standardized network. In summary, coax cable may be tested simply for cable integrity, but deformations in an intact cable can cause slow signal degradation. Wire map testing of twisted pair cable verifies that The most common cable faults are not present. Further testing for crosstalk, attenuation, skew, and other conditions verifies the quality of the signal path, and cable plants must be tested to standards, which verifies that the installation will work, not only for the current user, but for future users as well. That's it for testing voice, data, and video cabling, and I'll see you again for Chapter 10.